Okay, now shift your attention to security because none of this matters if the gateway becomes an attack vector. So the core idea is layered defense. You assume any single control can fail, so you can stack them. Okay, let's continue. Physical separation between OT and IT reduces blast radius, and VLANs create logical boundaries. Firewall rules default to deny because in industrial environments, silence is safer than openness. And unidirectional gateways and air gaps are extreme, but they exist for a reason. Some systems are too critical to risk bidirectional connectivity. So here devices authenticate with certificates because the passwords do not scale. Humans use multi-factor authentication because credentials leak. Role-based access control ensures operators, engineers, and administrators can only do what they are meant to do. Service accounts prevent applications from sharing identities. Okay, and here, let's continue. So here encryption, TLS 1.3 protects data in motion, and VPN tunnels secure remote access paths. Encryption at rest assumes disks will eventually be lost or stolen. Secure boot and TPM ensure that even if someone has physical access, they can't easily tamper with the system without detection. And finally, monitoring closes the loop. Logs feed into CM systems, and anomaly detection watches for behavior that doesn't match the baseline. Audit logs create accountability. Incident response plans exist, so decisions are made calmly ahead of time, not emotionally during a breach. Okay, and what's next? Predictive maintenance or PM. And yes, let's stop like that. Now, look at that. Start on the far left with sensor data. We deliberately combine vibration, temperature, acoustic, and current draw. No single sensor is reliable on its own. Bearings can fail quietly, motors can overheat slowly, and electrical issues often show up as subtle current changes. The logic here is sensor fusion. Each signal captures a different physical failure mode. Okay, and before any intelligence happens, the data is conditioned. Filtering and amplification clean the signal so the model is not learning noise. ADC here. Conversion at 24 bits ensures resolution is high enough to capture early degradation, not just catastrophic failure. And time synchronization matters because vibration spikes that don't align with temperature changes often mean transient events, not real faults. And sliding buffer of 1000 samples is the memory of the system. Without enough context, prediction is guesswork. And feature extraction, and this is where engineering intuition meets math. In a time domain, metrics like RMS, mean, and standard deviation tell us about energy and variability. In the frequency domain, FFT and peak frequency reveal imbalance, misalignment, and peering defects. Statistical features like kurtosis expose impulsive events that average height. And spectral entropy measures signal complexity, which tends to rise as components degrade. All of this collapses into a normalized feature vector because ML models don't understand physics, they understand patterns. Okay, and the model running here is TensorFlow Lite, not full TensorFlow, and that choice is intentional. So quantized INT8 models keep memory low and inference fast. When the diagram shows a 500 kilobyte model, that's not a limitation, that's a design goal. Okay, and the failure prediction outputs a probability between 0 and 1, and that number alone is meaningless unless you interpret it. So anomaly detection runs in parallel using a z-score approach, and remaining useful life estimation translates probability into time, which humans can actually act on. Okay, and the system doesn't just say something is wrong. It classifies health as healthy, warning, or critical. That abstraction is important or crucial. Operators don't want probabilities, they want guidance. And here actions. Notice what happens next. Alerts go to dashboards for visibility, emails and SMS escalate urgency. Work orders integrate directly into CMMS systems, so maintenance becomes proactive, not reactive. Data logging closes the feedback loop by storing outcomes, which improves future models. And system performance metrics, look at that part. The metrics at the bottom are not marketing numbers. Now, inference latency under 12 milliseconds proves this can run on ARM hardware. And CPU and memory usage show it won't starve other gateway services. The business impact metrics explain why leadership funds these projects: reduced downtime, lower maintenance costs, longer equipment life, and measurable ROI. Okay, and coding part again. So the script starts by importing NumPy, SciPy, and TensorFlow with runtime. This tells you immediately that training happened elsewhere. The edge only performs inference. That separation is intentional for security and performance. And when the engine is initialized, the TensorFlow interpreter is loaded and tensors are allocated. This is a one-time cost, not something done per prediction. The sliding window buffers are implemented using dequeues, which guarantee constant time, inserts, and bounded memory. So the failure threshold is explicitly set to 70%, which encodes a business risk tolerance into software. We can continue. Now, look at that. This function mirrors the diagram exactly. Mean, standard deviation, peak, and RMS capture vibration energy, and the FFT identifies dominant frequency, which often correlates directly to mechanical faults. Temperature features include rate of change, because rising temperature is often more dangerous than high temperature. Acoustic features add another dimension of anomaly detection. Spectral entropy is computed using the formula, and that epsilon avoids numerical instability, which is the kind of detail that separates production code from examples. At measurement, yes, and okay. Periodic failure. Prediction only runs once the buffer is full. That prevents garbage predictions during startup. The features are reshaped to match model input, tensors are set, and inference is invoked. The model returns a failure probability, which is then compared against thresholds. If the probability exceeds the critical threshold, remaining useful life is estimated. This is where raw ML output turns into actionable planning. Okay, and okay, estimate remaining life. The remaining life estimation is intentionally simple here. Higher probability means fewer hours left. In real deployments, this is replaced with survival models or degradation curves, but the structure stays the same. Right. And parallel to ML, a baseline is established using historical data. Anomalies are detected using a z-score, which asks how many standard deviations away from normally current value is. Redundancy matters. If the model drifts or encounters unseen conditions, statistical detection still provides a safety net. And example loop here that shows how this runs continuously. Measurements are added in real time. Predictions run every 100 samples after the buffer is full. The sleep of 10 milliseconds approximates a realistic sampling rate. And this is not batch analytics. This is live streaming intelligence. Okay, now performance optimization part. Here, the first thing to understand here is that gateway performance is not about raw CPU speed. It's about efficiency at every layer. And when you see protocol efficiency mentioned, the reasoning is simple. Binary protocols like Modbus or OPC-UA binary move fewer bytes for the same meaning. Fewer bytes means less network congestion, low latency, and more predictable behavior under load. That predictability matters more than peak throughput on a factory floor. And now think about data filtering. Most sensor values barely change from 1 second to the next. That band filtering takes advantage of that reality. If nothing meaningful changed, nothing gets sent. Batching builds on the same idea. Instead of paying overhead for every single reading, you amortize that cost across many samples, and the gateway becomes selective instead of chatty. Okay, and compression is another lever. Time series data compress extremely well because it's repetitive. Applying compression before transmission dramatically reduces bandwidth usage. Store and forward solves a different problem. Networks fail. When they do, local buffering keeps the system honest. And data is delayed, not lost, and that distinction is critical for audits and root cause analysis. Okay, and MQTT quality of service levels encode intent. Telemetry can be best efforts. Events deserve acknowledgement. Commands require certainty. Persistent connections remove unnecessary handshakes, which reduces jitter and CPU overhead. And these are small decisions individually, but together they determine whether a gateway survives peak load. And okay, now shift to lifecycle thinking. Industrial gateways are not disposable devices. They live for years. Firmware updates must be remote, safe, and reversible. Over-the-air updates with rollback protect you from breaking hundreds of devices because one of bad image. Certificate management is about time, not encryption strength. Expired certificates cause more outages than attackers ever do, and automation prevents that class of failure entirely. So, configuration backups are insurance. You hope you never need them, but when you do, nothing else matters. Health monitoring turns the gateway into a first-class asset. CPU, memory, disk temperature, and network stats tell you when hardware is aging or misconfigured. And logging ties everything together. Structured logs allow machines to read what humans used to scan manually. And capacity planning is humility encoded in process. You assume growth will happen and you leave headroom. That 30% buffer is what keeps normal growth from turning into emergency incidents. Okay, now let's ground this in real applications. Gateways sit at the center of smart manufacturing because they speak both languages, mission sickness and business systems. Overall equipment effectiveness is a prime example here. Availability tells you if machines are running. Performance tells you if they are running at the right speed. Quality tells you if they are producing value. Gateway collect all three without human intervention. And predictive maintenance builds directly on vibration, thermal, oil, and acoustic data. Energy management does the same with power measurements. Once data is contextualized at the edge, optimization becomes continuous instead of reactive. Okay, and energy management here, and here quality management, assets, environmental. Okay, now quality management relies on traceability. Asset tracking depends on location and state. Environmental monitoring enforces safety and compliance, and these look like different problems, but they are they all share the pattern. The same pattern: collect locally, contextualize early, act quickly. And some industry-specific applications here. And here, automotive focuses on robotics and traceability, as you can guess. Food and beverage emphasize temperature and batch integrity. Pharma care about audit trials and clean room conditions. Semiconductor fabs demand thermal communication and real-time dispatching. The gateway adapts, but the architecture stays consistent. Okay, another diagram. Can you see quality? That's good. Okay, look closely at the OE calculation flow. PLC signals indicate whether a machine is running. Production counts tell you output. Downtime events explain losses. Speed data compares actual cycle time to ideal. The gateway turns these raw signals into state, time tracking, and aggregated counters. And availability is running time divided by plant production time. Performance is ideal cycle time times count divided by running time. Quality is good parts divided by total parts. OE equals A times P times Q. And this multiplication is intentional. A weakness in any dimension drags the whole score down. And in the example shift here, you can see how this plays out numerically. Losses accumulate quietly. The final score lands below the world-class target, and that gap becomes an improvement roadmap instead of a value complaint. And I think, yes, another code parts here. Now, what you are looking at first is not a toy example. It is a production-grade OE engine designed to run continuously at the edge. It starts by setting a foundation of time awareness, logging, and state control. The reason time and logging are initialized immediately is simple. If you can't trust timestamps or trace behavior later, every metric you calculate becomes suspect. Now, the machine state model is the backbone of the entire calculation. Running, idle, setup, breakdown, maintenance, and no operator are not arbitrary labels. Each one carries economic meaning. Some states count against availability, some are expected, and some reveal systemic issues. Encoding them explicitly prevents ambiguity later when numbers are questioned. Okay, that's done. And look at that. When the calculator is initialized, three parameters matter more than anything else. Machine identity, ideal cycle time, and planned production time. Now, ideal cycle time defines what perfect performance would like. Planned production time defines what availability is measured against. Everything else is derived from these two anchors. And the internal variables reveal the philosophy of the design. Instead of sampling aggregates occasionally, the calculator tracks state transitions, counters, and timestamps continuously. This allows losses to be attributed precisely, not just after the shift ends. And starting a shift resets both time and intent. The shift start timestamp becomes the reference clock, and all counters are zeroed deliberately. And this ensures that yesterday's problems do not contaminate today's performance. And change state method. This is where availability losses are actually measured. Every time the machine changes state, the calculator measures how long it stayed in the previous one. The key insight is that downtime is not inferred. It is measured directly using the time in state equals now minus state start time. Okay, and planned states like setup and maintenance accumulate separately from unplanned states like breakdowns or missing operators. That separation is what allows availability to be both fair and actionable. And record part. And here performance and quality are captured at the moment a part is produced. Cycle time is measured as the delta between part timestamps, not assumed. Total parts always increase, but good parts and rejects diverge immediately. This is how quality loss is quantified without human reporting. Okay, and now availability is calculated as like that. Planned production time minus unplanned downtime divided by planned production time. Notice what's excluded. Planned downtime is not treated as a failure. This keeps the metric aligned with operational reality instead of punishing good planning. And that performance compares theoretical output to actual output using that. What is that? Ideal cycle time times total parts divided by operating time in seconds. The result is capped at 100% intentionally. Running faster than ideal may feel good, but it usually signals quality or wear risks. And quality is the simplest dimension conceptually, but often the most expensive operationally. It is calculated as good parts divided by total parts. Every reject hurts twice, once in wasted material and once in lost capacity. And calculate OEE, OEE is computed as availability multiplied by performance multiplied by quality. This multiplication is unforgiving by design. Excellence in one area cannot compensate for failure in another. The structure forces balanced improvement instead of local optimization. And output things, the return data is not just a score, it's context. Percentages are paired with raw counts, average cycle time, and detailed downtime reasons. Okay. At example usage part. The simulated run shows how this behaves in real time. Setup consumes plant downtime, production generates cycle times and quality variation. A breakdown injects unplanned downtime with a specific reason. When the machine resumes, the system continues without losing continuity. And this is exactly how real shop floor behaves. And the final parts now, ROI, return of investment analysis. We move from operational truth to financial impact. Now, ROI is the arithmetic consequence of better decisions made earlier. Reducing unplanned downtime pays back immediately because lost production minutes are usually the most expensive minutes in the plant. Improving OEE even by a few points compounds across shifts, lines, and weeks. Yes, and their energy savings come from visibility and control, not new hardware. Quality improvements reduce scrap and rework, which directly frees both labor and material. And labor efficiency gains appear when data collection disappears into automation. And inventory reduction happens when work in process is visible instead of guessed. And final part here, final insights, is about sequencing, not technology. We have talked about technology a lot, and starting with the biggest pain points ensures early wins. Piloting before scaling limits risk. Engaging operators converts metrics from surveillance into tools, and the standardization lowers long-term costs. Baselines turn improvement into proof, and iteration keeps value expanding instead of stagnating. And thank you for listening.